We need to find electric potential at any point of the electric type. It's an electric type. Charge at A is minus Q. Charge at B is plus Q. Central point of the dipole is O to A. Distance is smaller ray. O to B also smaller ray. So AB equal to A. So A equal to OB equal to A. That EP is equal to 2A plus minus B. Dipole length. Dipole moment. P is the product of dipole length with charge. Electric potential at any point around the dipole. So any point means it will not be equatorial or axial line. You take any point, let the point be C. The distance from O to C is R. Since there are two charges around point C, there will be two potentials due to minus Q and plus Q. So for convenience, we are taking the distance from B to C as R1 and the distance from A to C as R2. When you find potential, you need to take R1 and R2. So we need to find R1 and R2 in terms of R first. So that the angle made by the dipole or dipole moment with OC is θ. Drawing a 90-degree line from B to R. It's 90-degree right triangle. So this point is M. For a short dipole, for the point R is very, very large. BC is approximately equal to MC. Practically, the altitude and hypotenuse of the right triangle will never be equal. But if the base is small, it's a right triangle, the altitude will not be equal to the hypotenuse. But if the base is small, like you can see, the altitude can be almost equal to that. Okay. So if this distance base is very small, here this MB is very, very small, you can take BC approximately same as MC. If it's very large, it will be totally different, but it has to be very small. That's a condition we are taking. So R1 is exactly same as BC. So, but it can be approximated as MC. So MC can be written as O to C minus OA. O2C minus OM will be MC. Now, from triangle OMB, triangle OMB, cos theta, this is A, it's also A. Cos theta equal to adjacent side OM by hypotenuse O. OB is A. So we can find OM equal to A cos theta. Transfer this to the right. We substitute OM here. We get R1 can be approximated as OC, which is R, minus A cos theta. Similarly, when you extend this as a dotted line and get another 90 degree from A, this angle is theta again, vertically opposite angle. So this point is N. So R2 is exactly same as AC. R2 is exactly same as AC. That can be approximated as NC for large distance. So this can be approximated as NC, which is OC plus point. This will be from O to C, this distance straight, plus point. That will be the distance AC. So like last time, this theta you can find from this right angle. Again, cos theta will be adjacent side, which is ON, by hypotenuse is A. So you can get ON is equal to A cos theta. So here, R2 is approximated as OC, which is R, plus A cos theta. Now we can do the normal procedure. Potential C is sum of potential C due to B plus potential C due to A. So 1 by 4 pi epsilon 0. Now at C due to B, the charge is plus Q, where the distance is CB, CB which is R1, plus 1 by 4 pi epsilon 0. The charge is minus Q. We should take negative charge for scalar quantities like potential, but vectors, forces and electric field, we don't take minus, which is replaced by direction. This is distance from A to C, which is R. The common factors are out. Q common, 4 pi epsilon 0 common. What is left is 1 by R1 negative 1 by R1. We take LCM, that will be equal to 2 by 4 pi epsilon 0 into R2 minus R1 by R1. We substitute R2 and R1 values. Potential is equal to Q by 4 pi epsilon 0 into R2 minus R1, R plus cos theta minus R minus A cos theta. So R get cancelled. It will be 2A cos theta by R1 into R2, like A minus B into A plus B, which is A square minus B square. So R square minus A square cos square. 2A into Q can be replaced as dipole moment. So we get V equal to P cos theta by 4 pi epsilon 0 into R square minus A square cos square theta. And for a short dipole, this AB will be very, very small, fractional values. So you can neglect A square compared to R square. So for a short dipole, the A square part will be very, very small compared to R square. So A square can be neglected. The contribution to A square will be very, very small, fractional values can be neglected. The expression for potential will come as P equal to P cos theta by 4 pi epsilon 0 into R square minus A square cos square. In this, it's very clear. The electric potential is directly proportional to dipole moment. Now, if you take the point along the equatorial line, the theta will be 90 degree. Cos 90 will be 0, so potential is 0 along the equatorial line. For the axial line, theta will be 0 for 180 degree on the back side. Right side near the positive charge, theta will be 0, cos 0 is 1. Negative side will be cos 180, which is minus. If you take along the axial line, you will be plus 2. Theta will be 0. In that particular time, it will come as B equal to P divided by 4 pi epsilon 0 into R square, because we neglected S square with R square. So that we can maybe remove from here. It's neglected. It's clear. V is proportional to 1 by R square, or V is inversely proportional to R square. Along the equatorial line, theta is 90 degree. It's 90 degree. Cos 90 is 0, so potential is 0 along the equatorial line. If it's axial line near the negative charge, only difference is theta is 180 degree minus P by 4 pi epsilon 0 R square. Still V is proportional to 1 by R square.